present company, I feel fairly safe in the assumption that we're all pretty convinced that parallelism is, in general, not a bad idea. In fact, quite useful at times. But also, I feel fairly comfortable assuming that we all sort of understand that parallelism, especially in its traditional forms, can be quite difficult to really introduce. So, of course, over the past few decades, I think, there have been lots of work on this to help facilitate parallelism. And some, for example, right. So yes, so some, for example, are algebraic skeletons, as I'm sure you will recall, are high-level composable patterns of parallelism. So they abstract away the more low-level mechanics that are often a source of error and trouble and complication in one's life as a parallel programmer. And one nice thing, or a couple of nice things about algebraic skeletons is that they're fairly generic, or in that they're very generic. So you can have multiple different possible implementations, and you can have and these implementations can either have different patterns, say you've got a reduce, map, so on and so forth, but also that you can define implementations of these skeletons for different architectures as well. So GPUs, for example, higher performance computing, distributed computers, and all of this sort of thing. So they're quite flexible, and that's very handy. So the obvious and standard example, which I'm sure you've all seen by now, is the parallel map, which, as you would expect, does precisely what you would expect it to do. That is, apply some function or some operation to each element in the input, and that operation needs to be each mappable computation needs to be independent of the other computation. And we can do this in parallel. We can do this on however many cores you have, and so on and so forth. So, of course, as a parallelism talk, no parallelism talk is without its example. So we've chosen some other good old-fashioned one from the parallel set of from the no-fit suite, and this. This is actually fairly standard. I've just adjusted it very slightly to make it a bit clearer for the slide. So in this version, the inputs are chunked, for example. So we're chunking a list of integers. We're doing the sum Euler on each of those chunks, and then we're summing the result of that together. So perfectly simple, nothing you haven't seen before. And this has been parallelized using the strategist library. So yes, we're using the parallelist strategy, which is equivalent to the parallel map skeleton, and that's parameterized by our deep seek, which I'm sure you'll recall basically tells Haskell to actually do the job and not be lazy. Or at least that's the idea. Whether or not it listens to us is another matter entirely. So, of course, again, another staple of a parallelism talk is the speed-up graph. So, as you would expect, some Euler, especially from an example in the no-fit suite, gives us quite nice speed-ups. This is on our experimental machine called Reckon. It's a 28-core machine. It's up to 56 hyper-threaded cores. The dashed line, which you may or may not be able to see, you can probably see that, is the point where the physical cores goes into the virtual. And as you can see, for different numbers of n is a multiple of thousands, I should note. We get quite nice speed-ups. And of course, this is not alone. We've got there are lots of other examples where skeletons have been used to parallelize things and have gotten quite nice speed-ups. So this is nothing new, and it's quite nice regardless. So the thing with skeletons, though, is that because they are an explicit mode of parallelism, we still do need to put them in our code to use them. And this can be awkward at times. So skeletons, at least in the functional world, are often implemented as higher-order functions, as I'm sure you're aware. So you can pass in and so you can pass them around, and you can pass in the functions and the inputs and so on and so forth. And because these are implemented as higher order functions, you can, many of these have obvious, or sometimes obvious, sequential equivalents, and we usually call these recursion schemes. So things like map, fold, scan, even things like unfold, or anamorphisms, is I believe the fancy term for it, seeing as we're in Oxford. So we might as well use the fancy terms. So yes, so these obvious sequential equivalents, and this is quite handy, because what we can do is we can use these sequential equivalents as loci of potential parallelism. So yes, we're happy, we can go home, everything's lovely, because we can use this a parallelizing compiler, such as ScaleML, I think it's called, by Michelson and Scape. Or there was a paper last year at ICFP from David Castro et al. That deals with using anamorphisms, I think it was, to calculate how to use this. So using these recursion schemes as loci are quite handy. Now, of course, I'm not advocating that we should parallelize every recursion scheme that we find in our code, because that would kind of that would probably not help us very much. In fact, it would. Well, we don't exactly want to parallelize a show method or something, do we? You can imagine the overheads would eat into our own speedos. So, but as long as we have as many of these as possible, and preferably as restricted as possible, so using a map when you could use a map or a fold, for example, we know what components we have, and we can pick and choose what we want to use. So that's all very well and good. Unfortunately, there's a bit of a downside. So there is no strict guarantee that these recursion schemes will be evident or will occur in the code in the first place. And of course, as an extension to that, there's no necessary guarantee that the programmer is going to use the most restricted. So they might use a fold and they could use a map. And so, by way of example, we take the trusty no-fib suite again. So we've got the spectral set alone, which has 48 programs. It's written by multiple people, including most likely several people in the audience, like at least one. And all of these programs are designed for different things. They're all written in different ways. Excuse me. And at least 19 of these alone, in this relatively small set of relatively small programs, have at least one function that can be rewritten as a recursion scheme. So if we expand this out, you can imagine how many we may be missing. So why might a programmer not put this in? I mean, we all know about these things, we might as well put them in. Well, sometimes you'll find, one reason might be because the explicitly recursive approach is considered clearer in its intent, in how it's written, as opposed to, say, an historic composition of folds and maps and scans and things. Alternatively, and related to this, they might be from an earlier implementation. So, I'm sure you all know how it's like. You come along, you try to work out how your program is supposed to work, and then maybe you can go back and tidy it up and so on and so forth. And related to this as well is that some of these patterns, unlike map and fold, are not always going to be as obvious or as well known. So the unfold, for example, is definitely less well known than the fold, and there are a whole zoo of these morphisms that we get before. So yes, and of course there's also the problem of near patterns. So you might have a stray function at the end of your fold, which is obfuscating the fact that it's a big fold. So what would be nice is if we could actually discover these and discover the right ones and introduce them into the code relatively, not relatively, actually, automatically. So yes, that would be awfully nice, wouldn't it? But how are we going to do this? So let's return to somewhere, and let's assume that this is the definition that we were actually given rather than parallel definition. And so here I've used the pointer, can't I? Yes, there we go. There we go. So the as pattern here, I'm just sort of using as an implicit labeling so that we can refer to the list argument. So somewhere that does exactly what we expect it to do, and it does the same thing, albeit we're expecting just a flat list of numbers now. So in our parallel version, the Euler operation was lifted into a map. So how are we going to find it? Well, one thing we could do is we could use a technique of program slicing. Now I believe, I think it was on Monday, yes, there was a talk at ICFP, if you happen to be there, on program slicing. But long story short, program slicing first introduced or developed or whatever by Mark Weiser in 1980s, 1970s or something. He originally designed it for debugging. So the idea of a program slice is to remove all of the expressions in your bit of code or in your program or whatever that are not influenced or are influenced by a certain value in that same bit of code. So let's take someone, for example, and let's say we choose our slicing criterion, which is the bit we're interested in, is the x in the pattern range. So this one here. So yes, we've got that, and we can slice this using sort of standard slicing techniques, and we get something like this. So as you can see, we have removed the first clause because it has nothing to do with x. So this is actually a forward slice, if you want to be technical about it. And so we're the x highlighted is the slicing criterion. The x is the tail in the pattern match. Isn't used, doesn't appear in the slice because it has no relation to x. I suspect that's a dangerous thing to say, never mind. The Euler x in the right-hand side plus. So we've got the x in we've got the x here. That's the current, so we need to keep that. Likewise, seeing as this is so you've got so because Euler is applied to x, we keep Euler as well, and because Euler x is a in the slice and b an argument to the plus, we keep the plus as well. But we don't keep the recursive call because again it doesn't have x as a sub-expression. So this is all very well and good, but we still need to use this somehow. So what we could do is we could extend this slice, or narrow the slice further, shall we say. So what we're going to do is we're going to define a program slice as a set of variables, where inclusion in the slice indicates that that variable is used somewhere in the definition of the explicit recursive function that we are slicing. Now use, what we mean by use is basically whether it occurs as a sub-expression anywhere in the function. But also we have, and then we have the other idea is updated. Now, of course, in the functional languages, in most functional languages, variables are immutable. But we're considering as the value changes between successive recursive calls being updated that variable. And to very simply put it, we consider a variable updated when a recursive call is either recursing into that variable, so the recursive call is passed x's, for example, appending to a variable, so you're building the list, or is the same variable itself, because then you're just maintaining that same value. So that's, I should probably mention that in the full paper we do give sort of proper definitions of all of this, but I'm just trying to give an impression of it now. I think we've seen enough Greek over the past few days. So let's apply this to our sum Euler example, and this time we're going to choose the list itself as the slicing criterion, and we get back. Oh, sorry, I lied about the Greek. So the slice of sum Euler with respect to the slicing criterion, that is x is 0, is the set containing x and x's. Now, the reason why it contains x and x's is because x is 0 defines as part of a subpattern both x and x's, and both x and x's are used in the definition of some Euler. Now, we will note that x is 0 itself is not considered updated, thereby included in the set as annotated, because in the recursive call, we're passing in text, and we've said that this is okay. We also note that x is 0 is not itself included in the slice, because as you can see, it's not actually used anywhere in the... Oh dear. It's not actually... It's not on this one. Right, okay. What was I? So yes, it's not used anywhere in the slice. So to give an intuition, shall we say, for update, we can take a look at sum L, which is sort of a left with sum. So think of expressing sum as a fold L and then unfolding it in IN. Sorry, it gets confusing after a while. So yes, so again, slicing for x is 0, we get the same result. But for z, the initial or the accumulator variable, it's used because it's used in the first clause, but it's also used in the second clause, but it's also updated because we have this addition in the second argument of the recursive call. So this little bar over the z in the set there indicates that it is updated. So yeah, so this is how we define our slice. We define just a set of variables. So we still need to actually do something with this. We still need to infer which things are mappable, or which operations within our function are mappable. So how do we do this? So what we do is, because we're looking at the operation, so we consider an operation to be any function application sub-expression in the function definition that is not itself a recursive function. Because you can't map a recursive call. It doesn't quite work. So some Euler, for example, has the 2 plus an Euler. Simple so far. So what we then, so we're going to categorize each of these operations to see whether or not they can be put into a map. And we do this by looking at the arguments that it is passed. So if the operation's arguments includes variables that are both used and updated, then we don't consider this to be a mappable computation. So in the sum L, for example, we have the plus and... Actually, do I have that? Yes, I do. Excellent. So in the sum L, for example, we have the plus and the z. So you couldn't actually do that plus in a map because it shrinks the list, and whereas a map doesn't affect this fine. So good so far. And otherwise, so we consider these obstructive. That's just something we've categorized them into. And otherwise, we consider the operation unobstructive. So an unobstructive is basically the negation of this, but you can think of it as being, all of the variables passed to it need to be used but not updated, or updated but not used. So yes, we had sum L. And so let's return to our sum Euler example, our Barwell example. So we have the slice here. So x is 0 is the only argument. And so we're only looking at this one. And we've got x and x in the slice. So it's neither used nor updated, although it's reachable variables are. So that's very good. So we can look at both of the operations. So Euler first of all. Well, Euler only takes x, and x is only used. So this is good. So Euler is therefore unobstructed. Plus, however, takes plus doesn't take or its arguments aren't both used and updated. However, it does take a recursive call as its second argument. So therefore, we cannot consider this to be unobstructed. Instead, it is obstructive. I probably could have put that in a better way. So yes, so we've now found that our Euler x is a computation that we can lift into a map. So we're happy, we've found the thing. So of course, then what we can do is we can use standard techniques, say refactoring, lambda lifting, that sort of thing, to lift the operation into a lambda, which we can then pass to a map, and then we can pass that map to the rest of the function. This can all be done using standard refactoring techniques and things like that. And we can, of course, prettyfy this so we can realize that sum prime is the same as sum. And then we can chunk this, and because we know that sum is associative, commutative, etc., we can get back to where we started and we can therefore parallelize it. Now, of course, this introductory bit is sort of beyond the scope of the paper. In the paper, we're actually just focused on finding the map. However, I will say the introducing the map bit is described in my thesis, which I should be submitting very shortly. So yes, if you're interested, wait a few months. So we've, seeing as we've only got 5 minutes, I'll just go through this fairly quickly. So we've implemented a prototype of our approach. We've done this in Erlang for some reason. It seemed like a good idea at the time. Not having types is a pain. So yes, then we applied our prototype to 12 examples. These examples are from a range of things. So we've got 4 parallel examples, Sudoku, Someone, and MATLAB and Queens. 3 of those are from the no-fib suite. Sudoku, I think, is from Marlowe's concurrency in Haskell book. And then we've got several other examples just to demonstrate the approach. We have, so most of these already have the maps and things in them. So what we've done is we've unfolded them, and then we've seen whether or not we can rediscover the maps that we found. And we do. We find all of the maps we've unfolded in that we expect. Also, we time this, and our prototype is actually reasonably quick, which is quite nice. Although it does scale, I think it's quadratic. So it does quadratic with respect to the number of operations. So if you have a large thing, it could get a little. We're talking minutes here, sort of thing. But anyway, so obviously with everything there are a few limitations. So what we would like to do in the future is, of course, apply this to real-world examples. Also to real language. So at the moment, and as you'll see in the paper, we're currently defining this for a simplified expression language, which can effectively be seen as an intermediate representation of, say, like Erlang, Haskell, so on and so forth. But we would also like to extend it to arbitrary types. So to simplify our presentation, we restricted it to this. But there's no reason why you can't have the standard constructors. You just need to slightly edit the definitions of used and updated for those things. And of course, maps aren't the only schemes, although they are quite predominantly used in the parallel set. So it would be nice if we could find these other things like scans. Actually, I think the approach does or can effectively find zips. You just need a slightly different factoring, so that's good. But also actually look within the data structures themselves so that we can find more things like the Smith-Waterman example, or algorithm which populates a matrix. But we have difficulty with that because that's an example of a wavefront parallelism. So it would be nice if we can address those things. And so with all that, I think I have probably just about run out of time. 2 more minutes? Oh, I rushed for no reason. So yes, okay, so in the paper we present an approach to discover mappable operations in explicit recursive function. We've got a prototype of our approach. That's actually available. The link is in the paper. I think it's on my website somewhere. And we've applied this to a number of examples. But of course, we would like to go one step further and continue this. So yes, thank you very much. This is the scary bit.
So, given that this only recovers these recursion schemes, but it doesn't really give you any good idea of which ones to parallelize. So when you ran your parallel benchmark, where did the parallelization decision?
Well, the parallelism for the parallel benchmark, and all of them came from either the no-fib suite or Marlowe's book. So we were just testing those on well-known examples to make sure that we could find the ones we were doing. So for other programs, say for example ones that haven't been parallelized before, you can discover the maps in them, but we don't suggest to you which ones should be done. That's out of the scope of this particular part. So there is a fellow PhD student who was actually just recently submitted and moved down to Imperial in London. His thesis is basically on this. So looking at the available recursion schemes and playing around with the different configurations and working out using cost models. It's a dependency type system or something like that. It's a magic black box, basically. It discovers which ones are good, how to parallelize them, and will actually get you that way. So I'm purely interested in looking at the code, working out where we can introduce these patterns. Yes.
Can you comment on the relation about your work and what, if I am correct, it's called the third theorem of the isomorphism, like if you get a fold L definitional function and a fold R definitional of the same function, then you know that this function is a MapReduce combination. You see it on the fold L.
Yes.
So how exact is your technique and you can pull out the limitation?
Yes. So with the third homomorphism, you basically need to you need to have the two, and I believe there are papers out there which tells you how to get the right inverse from the left inverse, from the leftward fold. So if you have a fold, you can effectively you can then find the right inverse using. I can't remember who it is. It's one of the Japanese teams, but regardless, they seem to be pretty good at this sort of thing. But yeah, so they find the right inverse from the left fold, and then you can use the third homomorphism techniques to actually introduce the parallelism itself. So there are a number of sort of similar program calculation examples. I mean, you've got diffusion as well, and so there's quite a bit of work on this, isn't there? So looking onto this. But all of these so these are all sort of calculation approaches. So they sort of either require a specific data type, or they require that you have all of the information in the code or an external proof or so on and so forth. So mine, as we discussed in the previous answer, doesn't actually introduce the parallelism, but it can be used as a stepping stone for these other techniques. But also you've got so I mentioned the colleagues' system, but you can also use it for these other systems. But of course, there's nothing really stopping you from using this pattern discovery approach just for parallelism. I mean, you can use, so if you can find a fold, you know that your operation is trivially terminated. So you could potentially use this elsewhere. So I suppose the limitation here is that it doesn't actually introduce the parallelism itself. So I try to make no claim or no investigation about about sort of any of the properties needed to say the parallel fold.
But it reflects the map property.
Yes, it does. Yes. So if you have a mapping operation, you can find those. But yes, so I suppose.
In some sense, what it remains, it will be a reduced complete.
Yes, indeed. Yes. So that's part of the thing. So I've sort of been toying with this idea. So I like to think of it as you're sort of separating the wheat from the chaff, so to speak. And so the chaff left over. So there's somewhat of a primary example. My finger's gone down. Never mind. Now, presumably, if you can lift that map, that has to be a fold. I would assume I can judge it. These are crucified me for saying that. So presumably, all you then need to do is do a bit more work to work out what the arguments are for that fold, and do it that way. So what you could do is you could use a technique based on anti-unification, or indeed hierarchical unification. So there's a 10-year-old thesis by Andrew Cook. I think it was at Edinburgh. That uses. Sorry?
Harriet Watt.
Oh, Harriet Watt. Sorry, yes. I think it was one of the Edinburghs. So yes, he used that to effectively pattern match for this sort of thing. And there's a recent paper that uses anti-unification for the same thing that was recently published in FGCS. Which I saw on the internet the other day. So yes, so you could then use those sorts of techniques to work out what the to work out what the arguments are for the fault. So I suppose what you could do is for one stop, everything works solution, is you could use a number of these techniques in combination to effectively automatically introduce, so go from explicitly parallel code all the way down to nice and optimized parallel code. I think.
Thank you very much.